audible.
Okay, you start and you work from time to time, you watch.
Yeah. Okay. All right. Hello, everybody. Thank you for coming to my talk. Today I'll be telling you about supermassive black hole growth in massive galaxies at cosmic dawn. This is some work I've done with Ramon Tessier and Zach Andelman over at Princeton University. So just a brief recap over what we've learned over the past week is that we've been seeing a plethora of massive galaxies at cosmic dawn that are brighter than expected, as seen by the UV luminosity function here. These typical galaxies that are in excess have characteristic stellar masses, something greater than 10 to the 8 solar masses, and maybe a star formation rate above 1 solar mass per year. And what I really want to draw your attention to is the data at redshift 12 for the UV luminosity function, but more specifically, these contours of constant star formation efficiency that one would predict. And we can see that the data is kind of suggesting that there could be star formation efficiency higher than 5%, which is what we'd expect in the local universe, at least if you don't want to break lambda CDM. So I want to draw your attention to a bit of a theory that's been lurking in the shadows over the past week in different lectures. Many lecturers have mentioned the possibility of a somewhat exotic theory of how you might be able to get higher star formation efficiency in the early universe, and that's feedback-free starburst galaxies. This was first proposed by Avishai Deckel back, I think, in 2023 or maybe a bit earlier, and I just want to kind of demystify it for you. The general idea is that if you have a massive enough overdensity that's collapsing to form a halo that's about 10 to the 11 solar masses by redshift 10, then in principle you'll have really cold dense gas falling onto the halo and basically smothering this proto-galaxy. And what that does is it lowers the free fall time and the cooling time to be less than the characteristic time scale of the feedback, or of your stellar feedback. So you get some self-shielding, and you can actually raise your intrinsic star formation efficiency above 5% to even as high as 100%. And so you'd expect a prediction for a 10 to the 11 solar mass halo that you get something like 10 to the 10 solar masses in stars by redshift 10, and maybe a star formation rate of something between 10 and 100 solar masses per year. So these simulations that I'm presenting to you were first built by my collaborators, and then I joined on. But they use the AMR code Ramses that Yoki has talked about, or several lecturers have told us about. And these simulations are cosmological zoom-in. So we're simulating a single galaxy in a huge volume. The volume is about 100 co-moving megaparsecs. But we have an effective resolution physically of 10 parsecs within the galaxy. So that allows you to simulate the galaxy's interstellar medium and stellar feedback and physics and whatnot. So what really distinguishes this simulation suite from other simulations is our prescription for star formation. So typically, simulations will use a fixed star formation efficiency and assume a Kennekitt-Schmidt law to describe how stars form from cold gas. But for us, we're using a different subgrid model that uses physically motivated turbulence to predict multi-free fall timescales and whatnot. So what matters about that is that you get a non-fixed star formation efficiency within your galaxy, and you can get local star formation efficiencies something of the order 30% or higher. We have pretty standard stellar feedback. We implement photoionization feedback to inject thermal energy. This is like Stromgen spheres from your massive stars. And then we have core collapse supernovae, which can inject momentum and or thermal energy depending on if the cooling radius is resolved. And this is our galaxy in our giant box. So the upshot of when you put all those ingredients together is that you'll get a star formation rate and a stellar mass as a function of redshift that is pretty in line with what we see of the most massive galaxies that JWST has seen. But there's one crucial component missing here, and that's a supermassive black hole. So in the local universe, supermassive black holes are understood to have a really crucial and important role in co-evolving with their galaxy and influencing their host galaxy. So my work, or my contribution to this work has been to throw supermassive black holes in there and see what happens. So we ran a suite of numerical simulations. We have 10 additional simulations beyond the fiducial original simulations where we vary strength of AGN feedback, seed mass, the Eddington ratio. So 1 corresponding to the Eddington ratio, or like the Eddington limit, 3 meaning that the black hole can accrete 3 times that. And then stellar feedback, we have our fiducial model, but we also lower our stellar feedback. And if you have questions, I'm happy to explain how that works. But these are our suite, about 10 simulations. And what I really want to try and answer are these two questions. So I'm going to start with the first one, and that is, how is the galaxy impacted by the supermassive black hole within it? What we find, I'm just going to jump straight to the conclusion. There's no evidence of galaxy scale quenching, which is a bit contradictory to what one might expect. No matter what we tried to do, changing seed mass, changing like accretion rate and whatnot, there's nothing we could do to generate enough AGN feedback to quench the galaxy on the galaxy scale. And our explanation for this is linked to how fast the halo is growing. So coincidentally, at cosmic dawn at super high redshift, the halo is growing exponentially with a characteristic growth time scale that's comparable to the saltpeter time scale. And that saltpeter time scale, which is fixed, it's just dependent on physical constants, is comparable to the halo growth time scale. And that saltpeter time scale sets both the accretion rate of the black hole, but also how much luminosity it can generate through thermal AGN feedback. So basically, the idea is no matter what the black hole is trying to do, either by accreting gas or heating up gas, it doesn't matter because all the gas in the galaxy is going to be smothered by cold, dense gas accreting on by cosmic filaments, keeping a firm, strong reservoir of cold, dense gas to form stars. So the second question I really wanted to talk about is, how do supermassive black holes grow within this environment? There's a lot I could talk about here. I'm just going to try to distill it down to the most important points. Stellar feedback, once it turns on around 300 million years, or redshift 14, seeds a turbulent multi-phase interstellar medium with cold, dense patches and hot, diffuse pockets, which the black hole can meander its way through. And as the black hole enters into cold, dense regions, the black hole can feast, accreting maximally at the Eddington or super Eddington limit. And when it's not in those dense regions, it's basically starving. And so effectively, what you get out of that is a reduced accretion rate, like an effective accretion rate that is about half of what you would normally expect at a maximally accreting black hole. In other words, the black hole is starved about half of its existence when it's within the galaxy at cosmic dawn. And interestingly, I want to point you towards the fact that you see no difference in simulations with solid and dashed lines. A solid line indicates a simulation with AGN feedback, and a dashed line indicates a simulation without. And that implies that there's no self-regulation, and by self-regulation I just mean the black hole having an ability to mitigate how much it's growing through its own AGN feedback. You would expect these lines to diverge if that were happening, but we don't see that here. So what gives? Well, if we allow the black hole to grow more rapidly, either by increasing the Eddington ratio to allow for super Eddington accretion, or if we raise the seed mass, then what we find is that self-regulation can occur. The black dotted line is what we would expect from just a basic analytical model. I'm happy to explain why they're not exactly overlapping, but what's important is that we understand the shape and evolution of that self-regulated growth. And just for reference, I put some observations here. But what I really want you to take away from all of this slide is just that the black hole has to become massive enough, fast enough in order to achieve self-regulation at cosmic dawn. But if it does not do that, then it'll have to wait and basically catch the next train to become self-regulated around the Epoch of Reionisation. I'm happy to explain more about that. I don't have time, but feel free to ask me questions. I'm happy to explain that in a bit more detail. So let's leave you with my conclusions. Feedback-free starburst galaxies can achieve high star formation efficiencies when in simulations that are necessary to explain massive galaxies seen by JBST. AGN feedback cannot quench star formation on a galaxy scale due to rapid halo accretion in the early universe. Stellar feedback plays a crucial role in setting the ISM properties and how fast the black hole can grow or how much it's starved. And supermassive black holes can self-regulate at cosmic dawn, which was not necessarily a given, but they need to be massive enough to do so early on enough, or else they'll have to wait till much later. So that's my talk. Thank you.
Thank you. You might probably have already mentioned about it, but what is the mass range, the real mass range of the galaxies that you're considering?
The halo mass is 10 to the 11.
All right.
Yeah.
Yes. Yeah, a question concerning the simulation. So, what is the physical reason for which we should get to such high 30-40% efficiency that
So stellar feedback, or are you referring to AGN feedback or stellar?
For the first part. So
Yeah.
without forgetting the black hole.
Oh, okay. Yeah. So the simulations use a multi-freefall model, which basically the freefall time and the cooling time are less than the typical stellar feedback time, which allows for self-shielding. But sorry, I don't think I answered your question though. We should talk about it after though.
You're saying that you are modeling the AGN feedback,
Mm-hmm.
but what physics do you implement to all the small scale details, such as launching of jets, of winds, and so on?
This is a great question. So I didn't have time. I didn't properly mention how we inject AGN feedback. So we assume just simply a quasar mode, and we're injecting isotropically thermal energy into the through a mass depositing scheme into the surrounding environment. So there's no mechanical feedback in the form of jets in this. Yeah.
I have two questions. The first one would be, how long does simulation go? Do you do from redshift whatever until 0, or?
So the simulation stops at redshift 9. And then I can't remember exactly what redshift we start at, but I want to say it's like redshift, it's definitely above redshift 30 or 40, but like the time step, our fine time steps are of the order of 500 years. So it definitely, I can't remember the starting redshift off the top of my head, but it's a bit earlier than 15. It's just the black hole is seated at redshift 15, and so that's why I focus in on that point. But it evolves all the way up to 550 mega years.
Yeah, maybe we talk later.
Yeah.
Okay, thank you very much.
Which model you assumed?
Just Einstein de Sitter for this with like standard cosmology, I think. Good luck.
I'm getting there. Yes, but now I can't see where the extent is. Yeah, I got it.
Yes, that's right.
Oh. Am I at view? Almost. Is it this? Oh. The first one? This one? Perfect. We did it. Perfect. Hi, everyone. Thank you so much for staying all the way until Friday. My name is Claudia, and today I will tell you something about how proximate galaxies near high redshift quasars can reveal something about epoch of reionization. I'm not going to use the stick. I'm actually going to use the pointer. So I'm going to repeat a little bit of what we heard at the beginning of this week, which was that some of the key questions which remain in the early universe is what are the key drivers behind the epoch of reionization and what the ionizing output of these sources are. So first we need to know how much ionizing photons they produce. Then we need to know how much actually escapes from these objects into the intergalactic medium. Then we count how many sources we have, and we can figure out if we have enough photons from these sources to reionize the universe by the time that epoch of reionization ended. What's important to note, however, is that this number F escape times psi ion, is very often assumed to be this number or a similar number, where we assume that the escape fraction is about 10%, 10 to 15%. And this is because at high redshift, it's very, very hard to actually measure directly the Lyman continuum from these sources, because we can't see it due to the increased neutral fraction of hydrogen in the intergalactic medium. So if we cannot look at it directly, we need some indirect tracers. And if you paid attention to Laura's talk, you might be familiar with some of these plots. So one of the indirect tracer has been proposed to be a Lyman alpha, and that's because Lyman alpha is very sensitive to the presence of neutral hydrogen, which also blocks Lyman continuum. So if we look at the cross-section of this line, we see that whenever we encounter a neutral hydrogen with a photon that's right in the wavelength of Lyman alpha, we will immediately scatter. But we don't scatter just in space, we also scatter in frequency. And what happens slowly is that you get into the wings of the line, where the probability that you will be scattered by a neutral hydrogen is lower, and therefore you can escape. And this creates two escape channels, which is the red and blue wing of the Lyman alpha line. What happens is that then we see a very typical double-peaked profile of the Lyman alpha line in galaxies. At low redshift, about 1/2 to 1/3 of Lyman alpha emitters have this line profile. And the wider the peak separation is, the more neutral hydrogen is in these galaxies. And therefore, you are stopping almost all of your Lyman continuum escape. That's why it was proposed as a good indirect tracer of Lyman continuum escape, where the wider your peak separation is, the less you're emitting into the intergalactic medium. Now that's great, but what happens at high redshift is that the blue peak, which now would have a frequency higher than the Lyman alpha line, gets completely scattered by the intergalactic medium at high redshift. And therefore, finding double-peaked LAs is super rare. And if we do see them, can we be sure that the peak separation we're seeing is real? What if one of the peaks was actually attenuated by the IGM? Can we be sure? Well, I have good news, and it's that yes, we can be sure if we find a double-peaked Lyman alpha emitter in quasar-ionized region. So let's assume both of these galaxies are intrinsically double-peaked Lyman alpha emitters. In the non-quasar ionized region, we would see only the red peak, while in the quasar ionized region, we see both of them. Now, I said that the double-peaked LAEs are rare at redshift 5. These proximate ones are even more rare. The first one, forgot to say that we do see the real peak separation and equivalent width. But what's important is that the first double-peaked proximate Lyman alpha emitter was found in 2020, and it was found that it has too wide peak separation to have almost any escape. Now we have the second one. And the second one was found in 2024. It's at higher redshift, and when we look at the profile of its Lyman alpha line, we can figure out if it's a leaker or if it's not a leaker. Let's hope it's a leaker, but we'll find out soon. We were very lucky that this galaxy was found in a quasar that was part of the ASPIRE survey, so we have a lot of data. We don't only have the high-resolution spectroscopy of the Lyman alpha line, we also have the O3 doublet, as well as prism spectrum spanning from the Lyman alpha line all the way to the H alpha. So we can find a lot of information about this galaxy. When we do SED fitting, we can find the global properties of this galaxy. We see that it's extremely blue with a UV slope of -2.6, and it's also moderately bright. When we look at the mass, it's very low mass, very dust poor, and also metal poor. But the important question is this galaxy called LAE11 actually a leaker of ionizing radiation or not? Who thinks it is? We have 1 hand, 2 hands, 3 hands, 4. Okay, perfect. Who thinks it's not? Okay, 1, 2, 3. Okay, perfect. Well, I have good news. It does actually leak ionizing radiation. When we look at the peak separation, it puts it at about 18% leaking into the IGM. But we wanted to make sure that we are not biased in any way, so we used multiple tracers. All of them point towards ionizing radiation escaping at about 10%, which is great. And since we have access to other emission lines, sorry, forgot to say, these two are very exclusive to the proximate galaxies because we know we are seeing the full Lyman alpha line, and it's not attenuated at all. So because we have access to H alpha and H beta, we can also measure the ionizing photon production efficiency of this galaxy and arrive to what the ionizing output of this galaxy is. So if you remember the plot I had at the beginning, it said that the ionizing output, which is assumed, is 24.8. That's this line. And LA11 is almost there, but it's very close. But the epoch of reionization is not the only thing that double peak proximate LAEs can tell us about high redshift universe. We can also go and characterize the environments of high redshift quasars. So because this galaxy is sitting in an ionized region, we know that it's definitely in the quasar ionized cone, but we also see the quasar as a quasar, so we are also looking at it. And the triangulation of the quasar, of us, and the galaxy tells us that the opening angle of this quasar is about 50 degrees. It's a lower limit. Unfortunately, I don't have any more in this field, so I can't really tell if the angle goes wider or not. Another thing we can figure out is how long this quasar has been on. We see the quasar at the time of observation. But the galaxy, the quasar, the ionizing radiation must have traveled to the galaxy, ionized the region around it, and then the galaxy reports on the past activity of the quasar. And by finding the time difference between these two events, we can figure out that this quasar has been on for about 4 times 10 to the power of 5 years, which is very similar to other high redshift quasars. Another thing is that we can look at the star formation history of this galaxy. Now, all of this peak is the last 5 million years in the history of the galaxy. And by finding out what the UV intensity from the quasar radiation is at this point, and using some models, we can say that the star formation rate has been delayed until the point of the galaxy that we see. However, it's very hard to disentangle just stochastic way of forming stars from quasar feedback, so we are not really sure if the quasar is behind the star formation rates being the way it is, so I put a question mark just in case. And we are almost at the end of my talk, but I want to give a small sneak peek. So remember the first double-peaked Lyman alpha emitter that I said was found in 2020? It's this guy. We have data from the Large Binocular Telescope around new candidates around this field. And I found this. It's at about 8,000 angstrom, which would fit to the Lyman alpha region, which you would find at redshift 5.8. So maybe we will have another one, and we'll be able to put more constraints on the quasar environment itself. I'm going to leave you with my conclusions. Thank you so much for your attention, and I'm happy to take questions. There is one question.
Okay, no question?
Yes,
Yeah,
please.
So some double-peak Lyman alpha emitters in the literature have been shown to ionize their own bubble, so they don't need a quasar in order to have a double peak. Have you considered a scenario that the LAE is actually not right into the proximity zone and it's instead powering its own bubble?
So we have access to the quasar spectrum itself, and that shows the Lyman alpha line of the quasar. But then the ionizing radiation doesn't, or the radiation doesn't drop to 0 as we would expect from if the quasar ionized region wasn't affected. So by seeing transmission spikes to some distance, we can say where the galaxy is. The galaxy is sitting very close to the quasar. It's about 0.3 megaparsecs. So it's definitely in the quasar ionized region. Of course.
No more question? Thank you.
Thank you. Oh, I still have the microphone. Good luck.
Is it fine if I speak without a mic to everyone? Okay. Okay, for recording. Okay. I see. Okay, so good afternoon, everyone. I am Saksham Chandna, and today I'll be presenting my work that I have been following up with my supervisor, Dr. Simona Gallerani, and thank you, and Fabio Rimascia. And I'll be presenting on this fascinating new species of objects that has been discovered by JWST in the past 2 years, which are called little red dots. And by the way, this background of this image is basically the JADES deep field. So in case you actually find some unrecognized little red dots here, please contact me and we can write a paper together. Yeah, and we'll write another paper together. Okay, so, moving forward. First, some context. As has been clarified in this past week, that JWST has found an overabundant population of faint AGN from redshift 3 to 11, and with the black hole masses ranging from 10 to the power 6 to 10 to the power 9 solar masses, which can be noted over here in with the JWST faint AGN in this black hole mass to solar mass relationship, and also in the UV luminosity function, and 10 to 30% of these JWST identified AGNs are little red dots, as can be noted by that plot over there. But what are little red dots? I mean, if you have been living in a cave for the past 2 years, I'll help you out with that question. So, okay, maybe I won't, but yeah. So, what defines a little red dot? So, first of all, they are mostly compact and mostly unresolved. This can be noted here in this plot by the effective resolution limit of the 4.4 micron band of JWST NearCam, and most of these little red dots actually lie below the effective resolution limit. Then moving forward, they have a spectral V shape, which is a blue UV continuum and a steeply red in the rest frame optical, and this shape is particularly revolutionary because this has actually had a lot of consequences of inspiring researchers to actually look for this V shape everywhere and use that to identify little red dots. And yeah, congratulations, you know why it got its name as little red dots. Kudos to our imagination and creativity. So moving forward. And another thing is that they have broad emission lines, which so 80% of these confirmed little red dots have broad Balmer emissions. Additionally, they are noted to be especially weak in far infrared with non-detections with all these telescopes, which gives us upper limits on their dust masses and the dust temperature. They are also extremely weak in X-ray because there are no Chandra X-ray detections for these objects. They have some of them have particularly flat SEDs in the middle infrared range. So this could either imply that there is no AGN, or the AGN is without a dusty torus because there is no hot dust emissions. And additionally, one of the major important points is that they are really ubiquitous. They have really high number densities. So it makes it hard to reconcile these objects with some special kind of new species that has been found and that has never been seen before JWST. So what do? We try to answer 3 open questions, which is, what is the nature of these little red dots? Are these AGNs, are these star-forming galaxies, or are these due to the contribution of both? What are the physical properties that make a star-forming galaxy and an AGN look like a little red dot? And what are the observational diagnostics that we can maybe use to separate these different classes of objects that have all come under the umbrella name of little red dot? So what do? We take the already performed cosmological zoom-in hydro simulations by Gadget 3 from Valentini et al. And they have 2 suite of simulations that we'll be using, one of which has an AGN host, and they have black hole seeding and black hole growth, while the other is only star formation. To give some more context for those who are interested, it's a 3-particle mesh and SPH code. in which the dark matter subhalo on which they are zooming in is 10 to the power 12 solar masses, and the resolution of the baryonic particles and the dust mass is 10 to the power 5 solar masses, with the resolution being 0.41 co-moving kiloparsec. And the star formation recipe that they are using is using MUPI, which is a multi-phase ISM model, in which they are assuming a stellar efficiency of 0.06 with thermal and kinetic stellar feedback. And along with that, the black hole seeding prescription is basically that the dark matter halo with more than 10 to the power 9 solar masses will have a black hole seeded in it, and the seed mass of the black hole will be 10 to the power 5 solar masses, and the black holes can grow through black hole mergers along with Bondi-like accretion. And they also have a thermal feedback. So what we do, back again, what they were intending to do was basically create in 2021 the black hole mass to stellar mass relationship, which can be observed there. So I mean, but you can ignore all the points that are below 10 to the power 5 solar masses, because that was basically the seeding mass of the black holes. And what we do is basically take their simulation snapshots and we post-process them with dust radiative transfer calculations with SKIRT version 8 code. And how we basically do this is basically we take these two simulations, which I said were AGN FID and star formation only. We use redshift 6 to 9 snapshots, 23 snapshots in total. Then we move forward with like different kind of dust parameters. We use a dust to metallicity ratio of 0.1, which has been fitted to a redshift 8 through simulations of a redshift 8 galaxy, and also 0.3, which is a Milky Way like value. We use a dust mixture model, which is an SMC type and Milky Way type dust composition with Weingartner and Drain, but also a modified version which has a minimum cut on the grain size distribution as 0.1 micron, which is inspired by a lot of AGN detections with flat SEDs. Additionally, we use the emission SED that are explored. The stellar emission is coming from the Bujal-Charlotte stellar population synthesis models, and the AGN emission is coming from the Mache et al.'s AGN SED templates, of which we use two, in which there is AGN fiducial and a UV steep AGN SED. And this is actually inspired by theoretical and observational fits. So in total, we have these many different varying parameters which we will be varying, and so I totally perform 552 radiative transfer simulations in total, which then eventually we also, after the simulations are performed, we get a data cube out of the simulations, out of which we basically observe along 6 perpendicular lines of sight, with the spatial resolution being 58.59 parsec for both of these, and we mask around the central most massive black hole for the AGN FID simulations, while we mask around the center of the most massive halo for the star forming only simulations, which generates 3000 around maps and spectra for us to analyze separately. So what we basically do, using these maps and spectra, we individually analyze them as separate candidates for little red dots. We apply the Kochevsky's little red dot photometric selection criterion, which we consider to be the most recent, and that's why it is able to avoid most of the contaminant sources. And we make our conclusions based on that. So first we get these SEDs, which are color graded based on accretion the black hole accretion rate with respect to star formation rate ratio in the AGN FID and the star formation rate in star formation only case. And we are using the photometric filters, which are shown there in blue and red, and we are using the fluxes from those filters to actually fit it to this equation, and to calculate the rest frame UV and rest frame optical slope through chi-square minimization fit. Using these, we apply the Kochevsky's photometric selection criterion, and you can see over here, this is for AGN FID and this is for star formation only. The red points are the ones that are getting selected as little red dots, while the blue ones are failing the fit. But and you can see that 362 out of 1656 AGN FID objects are selected, and 135 out of 828 SF only are selected. The ratio is kind of comparable, but what that tells us basically is that both AGN FID, AGNs and star forming only galaxies can exhibit typical V shape of the little red dots. Additionally, we analyze their physical properties, and from the analysis, we also apply an ALMA upper limit on them. from which we can basically constrain a property, like they constrain their properties to a certain extent. But what that tells us is that the LRD-like AGNs are brighter, dustier, more star-forming, and more massive than little red dot-like star-forming galaxies. Finally, the most important result that we have found is that if we make a diagnostic plot of the flux ratios that are measured in ALMA bands and flux ratios from 2 bands in MIRI, and we plot these these little red dots that are powered by star-forming only galaxies and those powered by AGNs, we clearly note that there is a separation in these two, that they basically occupy different spaces in this flux ratio plot. So we can basically use this as a very good diagnostic criterion for future observations to separate these little red dot-like objects into AGNs or those powered by purely star-forming galaxies. And this is purely from continuum emission. So these are my conclusions, and in future we'll basically be working with emission line and nebular emission radiative transfer simulations as well. We'll be exploring many more photometric mass sizes and also implementing different Gaussian noise and PSF convolution to make more realistic maps to see how that affects the little red dot selection. And finally, we'll also be exploring different SED shapes in future. Thank you for listening. And yeah, yeah.
So I'm wondering why are you using photometric selection criteria to select your... You said you also get spectrum.
Yeah, I do. But the point was that at the end of the day, observers currently are using photometric selection criterions. The point was to see, because we don't know what these objects are. They could be a mix of a lot of objects. The point is to basically make as realistic maps as possible and select them as an observer would, and then see what kind of objects we basically end up with. So that's why we are using photometric selection currently, because there could, we also noted that it's also possible that a lot of these star-forming only cases are getting selected in photometric selection criterion because of the Balmer break actually coinciding with the photometric bands that are being used. So we are trying to make a conclusion that this is the subset that observers have actually found as little red dots, and what they have found could be classified into multiple different things. Yeah. Okay.
So, I mean, yes, okay, I agree, but there's also part of another group that use spectroscopy.
Okay.
So I think we should also check the spectra, because if you select from the spectroscopic side, for the star forming, you would not see broad lines in the, at least for some samples, you would not see broad emission lines, permitted emission lines. So I think the observers don't agree on this point themselves. So
yeah, that's true, but the spectroscopic conformations are mostly through broad emission line characteristics, right? The spectroscopic search for little red dots particularly.
Well, there is the compactness, the broad lines, and
yes.
the V-shape, and the slope.
And the V shape is done from photometric selection criterions. The broad emission line characteristics is also done with, so.
Yeah, then that depends which kind of criteria.
Yeah, because I'm not doing emission line radiative transfer over here for now, which I will be doing, and then I'll be using spectral. Yeah, we can discuss this later. Okay.
So, do you think the LRD, whether LRD is AGN or is SFG or both, it has a possibility?
I'm sorry.
Sorry, my bad. I mean, do you think little red dots are AGN or are star-forming galaxies?
The conclusion is that they can both be AGNs and star-forming galaxies, and by conclusion is basically to make a diagnostic plot or a diagnostic criterion that can be used to separate them based on their continuum emission purely, which was this plot that I was showing.
So what is the fraction? What's the fraction is AGN under?
The fraction is kind of quite similar, like almost like the total number of objects that we have analyzed, the total number of AGN objects that we had, the ratio of objects that were selected as little red dots is similar to the ratio of objects that were selected as little red dots for star forming only cases. So we can't really separate the two based on how many are AGNs and how many are star forming only galaxies.
May I ask from open, does the criteria of selecting agent is a Balmer Greek?
Yeah.
Yes.
I mean, for selecting little red dots is photometric, and it can also be broad Balmer emissions. But here we are not assuming anything based on that. I mean, it's only that the Balmer break is existing in a lot of these spectra, and some of it is actually coinciding with the photometric maps. And we are basically saying that a lot of the species that are also being detected by observers could be from these Balmer breaks. Yeah.
Okay, hi, I'm Maria. I'm a second-year PhD student at the University of Cambridge, where I'm supervised by Roberto Mailino. And together with Hannah Ubler, we've been analyzing this project where I study the gas phase metallicity gradients of high redshift galaxies using JWST. And Roberto already gave a very big overview of chemical enrichment at high redshifts yesterday, but I'm still going to go over the fundamentals again so everybody knows what's happening. So we have metallicities, which is basically the abundance of metals in galaxies or in the gas of the galaxies. And metals are just heavy elements, or basically elements heavier than helium, and we just sum them all up as these metals. And they're produced in the stellar interiors and then ejected into the ISM via supernova and stellar winds. And this whole interplay of gas being accreted and being ejected from galaxies is called the cosmic baryon cycle, as we've heard yesterday as well. So we have this inflow of pristine or metal-poor gas into the galaxies, which fuels star formation and at the same time dilutes the ISM, so decreasing the metallicity. And this new fuel of star formation obviously forms stars, and they produce these heavy elements in their interiors, as I said before, and then they enrich the interstellar medium through stellar winds and supernovae. And there's things like outflows as well, which can eject metals or enriched gas from the galaxies, decreasing the metallicity overall. This is usually due to AGN feedback or stellar winds. And then some of this material can cool down enough and be reaccreted into the galaxy as well. And the reason why I am so interested in this is because obviously the metallicity is directly connected to the star formation inside the galaxies and the gas flow. So it gives a great detail into galaxy evolution at high redshift and also how chemical enrichment happened in the early universe. And yesterday, Roberto introduced us to the different tools to measure gas phase metallicities. There's primarily electron temperature-based calibrations or those via strong optical emission lines. In my analysis, I only ever do strong optical emission lines as I'm not able to measure auroral lines. So to give a brief overview of the different categories of gradients, we have negative gradients, which is when we have a higher metallicity in the center and then it decreases radially outwards, which is usually attributed to an inside-out growth. So the center of the galaxy forms first and is metal enriched, and the outskirts forms later and is less metal enriched. Then we have flat gradients, which is not really a homogeneous distribution of metals throughout the galaxy. There's so much radial mixing going on, which is usually due to mergers and interactions and outflows and supernova and winds, that we just have a very chaotic distribution of metallicities, and therefore it's overall quite flat. And the last one is positive gradients or inverted gradients, which is when the center is less metal enriched than the outskirts, so it radially increases, and this is usually due to pristine pristine gas flowing into the center of the galaxies. To give a brief outlook as well on how this is currently standing in respect to redshifts. In the local universe, we kind of agree that there's mostly negative gradients, as this paper summarizes, as even through different stellar mass bins. So we usually see that the center is more metal enriched at the outskirts, which is probably due to over cosmic times, galaxies have more time to settle, and there's less mergers, for example, in the local universe. So the center just becomes more metally enriched. But then towards higher redshifts, we have a bit of a discrepancy. Recent observations like this one show that it's mostly flat, which is maybe what we kind of would expect for high redshift galaxies, since there's more mergers going on. Galaxies are more irregular in morphology as well. There's just a lot of chaotic things going on. So their observations show it's mostly flat. But then simulations for high redshift have shown that they actually become more negative as we go to higher redshift. So the main goal for my analysis is to use the sample of 7 low metallicity galaxies at high redshift between 7.2 and 9.5 to give more data points in the observational side so that we can get maybe more conclusions to this. So the 2 main goals is to study these metallicity gradients to get an insight into the early chemical enrichment. And since I'm using near-spec prism IFU, I also have spatially resolved data, so I can look at the resolved maps and actually specifically look at each galaxy in detail to see how well it is mixed or if there's actually a radiochemical structure. To give a brief overview of the sample, this is the global mass metallicity relation, where if you go to higher masses, we have an increase in metallicity. And my 7 galaxies are the ones in color here. The local relation is the black continuous line, and then I have 2 relations at higher redshift and then some data points at higher redshift as well. But more or less, I have a sample that is less enriched than the local universe, which is what we would expect at higher redshifts, and they more or less fit into other measurements at similar redshifts. So my metallicity kind of range between 12% solar metallicity down to 2% solar metallicity, which is quite low. Then the main point, yes, I have. The main point is the gradients, which I've shown here, and Roberto also showed it to you yesterday. So I have my main galaxies again in the same color, and you can also see it in the legend. All these like translucent points are observations for different redshifts, and as well as these like rectangles. And then all the lines in color are from simulations, where I'll still be adding more to them to make it a bit like even bigger overview of them. But basically, my gradients are very. There's no trend that I see, which is what previous people might have found. So, for example, this newer paper by Lee 2025, which is a few months old, they kind of found a trend where they did find more negative gradients to higher redshift, but I find no agreement for that. So mine are a bit all over the place. And to maybe give a bit of more insight, I want to show the spatially resolved maps for these 2 galaxies. So one of them is more a positive gradient, and the other one is a flat gradient. And first, I want to show the positive gradient. So to measure the metallicity gradient, I do concentric annuli. So I create these annuli, which are these dashed blue lines. And basically, within each annuli, I sum up the spectra. And the summed up spectra is where I measure emission lines. And then from these emission lines, I get the gas phase metallicity. And then I can plot a radial plot. And obviously, it will more or less. And this one is positive, which we can also see if we look more closely into the spatially resolved maps. So on the very left is the metallicity map. In the middle is the R3 ratio, and here's the neon 302 ratio. And we see that there's a lower metallicity in the center, and then it increases outwards, kind of showing that it's a positive metallicity gradient, which we would attribute to there being some kind of pristine gas flowing into the center of this galaxy. Then I also have this galaxy, which is more or less a flat gradient. And again, I'm showing the map on the left, which is very chaotic. there is somewhat of a increase in metallicity to here, and then an decrease in metallicity to here. What is very interesting about this specific galaxy is that we can also measure the metallicity for 3 satellite galaxies in the same field of view of this data, where 2 of these satellites are very low in metallicity, and one of them is somewhat half of the metallicity of the galaxy itself. And one of them, if you look at all of these plots for the right side here, is already outlined by the continuum contours, and then another one is outlined here. The third satellite is a bit further out, so it's not pictured here. But it would make a lot of sense that this galaxy could definitely be a flat gradient because of interactions with these satellites and gas exchange. So that gave us a great look. So a similar detailed analysis can be done for all my other 5 galaxies, although I did show you the 2 with the best signal-to-noise ratio and the best maps. The other ones are not as great. But yeah, I'll leave you with my conclusions. Thank you.
I'm just wondering, those morphology are quite complex, you know? So how can you be sure that you have the center of the galaxy at the point you choose? Is it the center by dynamical mass, or?
So the center for where I put, the center that I put for creating the annuli I get from the stellar continuum.
Oh, this one looks okay. Let's go to the next one.
Yes. This one?
Yeah.
I mean, these spaxels, I think, are mostly created already from the satellite that is there. So I think this is more or less actually like the morphological center of the galaxy as well. Yeah.
I'm not sure if I missed it, but do you compare with the distribution of star formation rate? Because I think, correct me if I'm wrong, that if you had like constant metallicity but a gradient in star formation rate, that would mimic a change in metallicity the way that you are measuring with the Stoney ratios.
Yeah, so far I only have the global staff measurement sequence as a plot ready. I already did resolved staff formation rates, but they don't look good yet, so I didn't put them on the slides since this is still ongoing work. For the global ones, we have high staff formation rates. It's what we expect, especially since I select low metallicities. For the maps with the resolved ones, I remember 2 of them, but they did look very more normal, where there was a peak in the center and then it decreases outwards. But
mimic the metallicity distribution.
I would have to do a deeper look. I only did these last week and then had no time.
So I have a question on the way you choose your concentric rings when you are calculating the stuff. Because, to me it seems a bit too small, considering the PSF of this.
Yeah, so the rings are all only 1 spaxel in width. And yes, I think the thing is, if I would select, for example, wider rings, I would just have 2 data points or something. Because honestly, this specific galaxy where I'm showing this is my best galaxy with the best signal. All the others have much less, are much less broad in their distribution. So I will have less data points already.
No, okay,
no,
you
okay.
got it.
Perfect. Okay, thank you for still being here. My name is Anita Schiller, and today we're going to be avoiding crowds with the question in mind of, okay, now this doesn't work, of how young cosmic voids already impact their galaxy populations. First, I will give you a quick recap and context for my work. So we're going to fly through the large-scale structure of the universe again. And we already know that galaxies reside within the filaments and the nodes of the cosmic web. And galaxies tend to avoid certain regions, which seem to be mostly empty. So what is a cosmic void? Generally, there's no unified definition for it. However, they describe underdense regions in the universe that are expanding with time, and as they expand, they become increasingly spherical. Now, what am I working with? I'm using Magneticum Pathfinder simulations by Dolak et al., which are smooth particle hydrodynamical simulations covering many box sizes with different resolutions. Since I'm going to take a statistical approach on voids, I will be working with box 2b, which is like a sweet spot between size and resolution. So the mass that can be resolved are 10 to the 8 solar masses, and the box size are 640 megaparsec. To give you a rough idea, I find 11 million halos at redshift 0 present within this box. So what do we know about the voids in the simulation? What you see is the radius of the void and the absolute count from redshift 0 to today. And it is apparent that the peak of the distribution shifts to the right with increasing time, which indicates that voids are growing, as mentioned before. And also note that the absolute count is going down with time, since voids tend to merge. So what do we know? Voids are underdense and growing regions, but are they empty? The quick answer is no. We find some void galaxies within observations, for example, SDSS, or also cosmogrid simulations. And what I want you to note is in this slice through the void, you still find a lot of inherent substructure going on. So just to have you to keep in mind that voids are not really empty, but there's still a lot of things going on inside. To convince you that I also find void galaxies within the simulation, I plotted the rate from the halo within a void, the radial profile, which shows the density in spherical shells from the halo. So note that after we encompass the halo, the density contrast drops below 0. And since it is below 0, this indicates that this halo actually lives within the void. So I hope you're convinced that void galaxies do exist, but now we're interested in how they differ. The main tool I'm going to use is the halo mass function. Just a quick reminder, it shows the account of masses within certain ranges, and we see that we have relatively more low mass halos than high mass halos. The thing I'm going to introduce you to are void halo mass functions, and I am going to spherically trace the halos within the simulation depending on their location within the voids. So I have 4 different void halo mass functions, and depending on where your halo is residing within the void, they will be counted towards the different void halo mass functions. I'm going to do a statistical approach, as mentioned before, so these are relative to the dependent void where the halos are residing in. Okay, so now what do we find? I'm showing you the halo mass function first for all of the halos within the box, including those within the nodes and filaments.
And we see this follows the shape I showed you earlier perfectly. But the interesting part now is what happens if I only have a look at void halos. So calculating this with all halos that reside within one void radius, we see that there is a drop in the high mass end of the halo mass function. This is due to the fact that we exclude all the most massive halos within nodes and filaments. If we take this even further, note that the shift starts to decrease. I don't know if you can see this, but for only 1/4 of the void radius, we see that the void halo mass function is cut way earlier. A quick refresher, the structure formation in the universe from a redshift 6 to 0. Note that at a redshift 6, the distribution is rather isotropic, and the cosmic web only becomes really pronounced at a redshift of 0. And this is what I'm going to be showing you with the void halo mass functions as well. So now we're going back in time. And what we see is that the void halo mass functions now are shifted towards lower masses, but still show this pronounced split up. And if we take it another step back, at redshift 4, you can see, again, less massive halos, but now the split up is not yet pronounced. So what is remarkable is that the 1/4 void radius halo mass function seems to not shift anymore between redshift 4 and redshift 2, meaning that the deepest inside the voids, the accretion of mass stops earlier. The same is true for the stellar mass function, so just for you to note. The summary now is voids do impact their galaxy populations, and I will give you a quick sneak peek into what I'm working on currently. So I'm tracing if global void properties have an impact on their populations, and I'm using the size of the void, the ellipticity of the void, and the density contrast. And what I want you to take away from this is there is no really an inherent split going on. Also, what's interesting is here's the star formation. The contours are all the halos, and the colors only void halos. And you see they follow the contours perfectly. So I don't seem to find any difference in star formation on cosmic scales. Now coming to my conclusions, what I want you to take away from this is we have an underabundance of high mass halos and voids, and there's no significant change of the innermost parts of a void after redshift of 4. Also, seemingly, global void properties do not impact the void halo mass functions, and also no impact on star formation rate. We might actually try and look at this in new upcoming higher resolution simulations called Dawn, and I will be very excited. Thank you.
So very interesting. So you said that after z equals 4, at the center of the void, there is almost no more accretion.
Yes.
So they are in secular evolution afterward, and are they in a really secular evolution mode before z equals 4?
Sorry, I didn't catch the last part.
Secular evolution. This is evolution of the galaxy alone, without majors.
Ah, yes. Yes, that's basically like a laboratory for having a look at isolated galaxies, yes.
And is it already secular before z equals 4, kind of?
I would say so, because the voids start to grow from the initial density fluctuations, so I would think so, yes.
So you said that the void radius grows over time?
Yes.
Do you know how much of this is due to just the universe expanding, and how much is it due to gravity pulling the non-voids closer together?
Since I'm using with co-moving coordinates, there is actually a growing going on.
question is,
Yeah.
could we get some information about the high redshift universe from these halos in void regions?
Do you mean on a cosmological scale? Or
I mean, we could observe these void regions and get information of high redshift universe, because I saw that these halos cannot grow much, or the galaxies inside could not grow much also. So I mean, whether we could observe these regions and get information about high redshift universe.
okay, I think it's hard to observe void galaxies in a statistical sample yet at this point, because they are mostly fainter than the galaxies in the cosmic web. I hope I understood your questions. Otherwise, we can talk later.
Okay, thank you again.
Okay. Hello everyone, I'm Riccardo, PhD student at Sapienza University of Rome, and today I want to talk about my PhD project on super Eddington accretion, and in particular about galaxy merger as trigger for super Eddington accretion. Let me start with a brief introduction. First of all, we know that JWST discovered this population of supermassive black hole at early age of the universe, at high redshift, and we know that if we model if you made a simple toy model of light seed coming from first pop-T stars, and we let them accrete at the Eddington accretion rate, we cannot explain this kind of discoveries. But we know that there are other kind of seeds, as Marta said this morning. So if we include in the picture these new seeds, like the medium seed coming from, for example, nuclear star clusters, or the heavy seeds coming from a direct collapse black hole, we see that in a sort of sense we could explain this kind of accretion. But we have to take into account that here we are considering accretion at nearly Eddington limited for a long period of time. So we are talking about hundreds of million years. So this could be in some kind tricky to achieve. What other models, or more realistic models, say about that? If we use some semi-analytical model, like the one of my group, it's called CAT. This is basically the same as before. We have the massive of the black hole and the redshift. We know that we see that if we use a Eddington limited model, we could not explain all the black hole we see at such high redshift. Instead, if we use a super Eddington accretion model, we could explain all the variety of JWST detected black holes. So, but this is a semi-analytical model. He has some, let's say, trouble that Marta explained very well this morning. So, what we started to do is to work with the simulation. So, we started with the simplest case possible. We made an isolated simulation in an idealized environment. So, a simple galaxy with pristine gas, and we put a black hole inside, and we allow it to grow super Eddington accretion rate. We change some parameters, like we vary the mass of the black hole, and we also vary the coupling efficiency, that basically is the quantity that regulates how much of the luminosity of the AGN goes into the gas surrounding him. So we use isolated simulation because this allows us to achieve some good spatial and mass resolution, and this is a video of the no feedback case. You see that basically the black hole, this is gas and this is stellar. You see that black hole initially eat all the gases, and you can see on the bottom the accretion rate varying with the time. So what are the results of this first simulation? We see that basically independently from the seed mass, we start from the 500 solar masses to 10 to the 5 solar masses, and we also change the coupling efficiency from 0 to 10 to the -3. We see that basically independently from this varying these parameters, at the end of the simulation, all the black hole goes to 10 to the 5 solar masses, more or less. And so this is really promising. But also in this isolated simulation, we lack for all the cosmological environment. So what I'm currently working on, and I'll show you some preliminary results, are galaxy mergers as trigger for this kind of super Eddington accretion. Why a galaxy merger? Because as we saw, we need a huge amount of gas, and also we need a high density in the central region surrounding the black hole to allow him to grow super Eddington. And galaxy mergers are good candidates because we see that when we have galaxy mergers, there is this inflow of gas, and also, especially major mergers, and also this is a process that can be repeated, because what stopped the black hole to accrete more in the earlier simulation was the fact that we simply lack of gas in the end. So what we did was to start with, I don't know if you see it. Oh, this is a dark matter only simulation. We made a zoom in. A lot of people today talk about zoom in, but for the people who are not into cosmological simulation, basically, okay, we start with a dark matter only simulation with really bad mass resolution and spatial resolution, and we, oh no, it's bad. You cannot see anything. Oh, okay. So this is the region of the initial box, and we zoom in to see the merger. This is the moment of the merger of the two halos. And this allows us to achieve really good final mass resolution and spatial resolution for the gas of order of the parsec. So with this setup, we made two initial simulations, changing the seeding prescription, because we saw that seeding is a crucial mechanism that could allow or not the black hole to grow. In the first run, we see the black hole in a halo when this halo reaches 10 to the 6 solar masses of stars. And in the second run, the same thing, but when a halo reaches 10 to the 6 solar mass in gas. So we expect this simulation to have way more black hole than the first one, because stars are more difficult to form than gas we have already at the beginning of the simulation. So what we see, I don't know if I can stop it at a certain moment. Okay, but we can see that in this simulation, first of all, we notice how due to the abundance of black hole, all the gas is more spread out. So we expect this to have a lower accretion rate with respect to the first one. And you can see here the inflow of gas I was talking about earlier. Let's see these first results. The first results, this is for the first run, the one with the two black holes. We see initial spikes, as in the first simulation, the isolated simulation. We see that all the black holes grow in the initial time step. We see initial spikes nearly to the Eddington limit, but we never overcome super Eddington accretion. but we discovered why. Unfortunately, in this kind of simulation, when you vary all these kind of parameters, you have to deal sometimes with luck, and we had bad luck because I don't know if you can see it. Okay, take a look. Now you will see a black hole here and a black hole here, more or less. The black hole are the red dot. See what happened in the moment, exactly in the moment when where they are seeded. You see the explosions. So we were unlucky because for our prescription of supernovae, they actually, a few time steps after we seeded them, all the supernovae exploded. So all the gas was spread out, and we could not achieve the super Eddington threshold. But we are confident that changes this kind of mechanism, we will see this kind of results. And for the second run, as we expected, we see that for all the black holes, there are dozens of black holes, we do not see ever accretion, let's say, nearly Eddington accretion, due to the fact that, as I was saying, the feedback from each black hole spread out all the gas, and we saw that high density of gas is necessary to achieve this kind of high accretion rate. So I leave here with my conclusion, with a picture of the final snapshots of the simulation. Thank you for your attention. Yes. This one?
Yeah, on the right panel, the top right one. There are some, so did you see so many black holes, or did I confuse it with something?
What, sorry?
The red dots.
Yes.
Are they like
The black holes, yes. Yeah.
you see like quite a few?
Yes, because here we see the black hole when a halo reaches 10 to the 6 solar mass in gas. So it's easier to achieve 10 to the 6 solar mass in gas instead, because to have 10 to the 6 solar mass in star, you need a lot of gas, and it has to collapse. It has to,
Additional question? Okay, thank you for the school and I know.
Yeah, okay. Hi, I'm Katharina. I'm a first year PhD student at the observatory in Hamburg, and I work with Jan Torge Schindler and Roman Meyer from Geneva and many others. And so, yeah, let's return for this very last talk of today to our favorite topic, the luminosity function. And since I only started like in May, I don't have a luminosity function to show you, but I will describe exactly how we get there, because even though we saw many over the last week, it's not very trivial to build one. And I also want to focus on broad line AGN, so the fainter sample compared to quasars, and I want to motivate like why this luminosity function is interesting. So if we look at this image here, so what we actually still do not know is what a fraction of galaxies do actually have accreting black holes in them. And so people who have estimated like the using different, building the different luminosity function with different samples, have estimated very different things. And so, as you can see, this doesn't really agree. People don't really agree on this. And so we also don't know, does this change with redshift, and so on. So the data I will be using is part of JWST Treasury program. So this is the Cosmos field. There actually have been already 2 programs within this Cosmos field with JWST. The first one was called Cosmos Web and did NIRCam and MIRI imaging in this orange field here. It's about 0.55 square degrees. And so Cosmos 3D is building on this data set. First of all, it provides other imaging in other filters, but also in filters that have already been observed to study the variability. But what is interesting for us is the slitless spectroscopy in this central field. So it's not the entire thing, but 0.33 square degrees. And if I am not wrong, this is the largest field that JWST has performed wide field slitless spectroscopy over. And so we have one filter, so we cover 3.9 to 5 micron at reasonable resolution. And so for us, we are looking for H-alpha lines, which means that we can probe broadline AGN in a redshift range from 5 to 7. Okay, so I want to focus a bit more on slitless spectroscopy. It hasn't been mentioned much. So the advantage of using this technique is that you can point your telescope at a field and you can get the spectra of all the objects that are in that field in this one observation. So this means that I can get a very large sample of spectra that are completely unbiased because I do not do any pre-selection. And so to give you a number, in theory, in the Cosmos 3D field, we could extract 650,000 spectra. But of course, this doesn't come with its own, it comes with its own problems. And so one of them is, okay, I can do the spectroscopy, but I have no idea which source I'm spectroscoping, let's say. So I need the image to cross-match which object has which spectra, belongs to which spectrum. And the second thing is 2 objects that are in the same, that lie in the same dispersion direction because you're just projecting the wavelength space across your detector can overlap. And so for us, this means because we're looking for emission lines, I can associate a line to the wrong object. So we need to be very careful in how we select our sources. And so in the Cosmos 3D collaboration, we have 2 independent data reduction pipelines, which in theory can take care of these 2 problems, except for the line confusion thing. That is still there. And so I use Grizzly. Maybe some of you know it because it's also used for HST data reduction, which is maintained by Romain, my collaborator in Geneva, and Gabriel from Copenhagen. And our colleagues from the US use JWST Unfold and do exactly the same thing as us. So another thing that is complicating for us, because we are looking for the H-alpha line, which is just a single line basically, is that this, if you remember, we have spectroscopy only in the one filter. And which means it's not broad enough to cover more than one line, especially if you're looking at H-alpha, which means that even though I see the line and I can model the line and determine the redshift, I still don't know if I have H-alpha at high redshift, or I have, for example, Paschen alpha at lower redshift, because both of them are Bramah lines, and we are not really sure how to distinguish them by their shape alone. Okay, so how do we then actually select this broad line AGN? So there are 2 steps I want to focus on. So the first is the pre-selection. So even though we have such a large sample of sources, actually this is a problem for us because, as I said, we might confuse lines of objects. So we actually need to visually expect ourselves every spectra to be sure that we are not mismatching anything. So the first thing we have to do is we have to reduce the sample size, and only then can we go on and say, okay, is this a broad line, is this an AGN, and so on. Okay, so a bit more detail about this photometric pre-selection. So the first thing we have to do is we have to ensure that our source is bright enough that we can have a reasonable spectrum. So we just set a few flux and signal-to-noise ratios on the data. And the second that we do, because this takes care of a few 100,000 objects, but we still have a few 100,000 objects left. So we have 2 other criteria. One is the color. So we compared colors of simulated galaxies. So on the one hand, the quiescent ones, which are expected to not have a lot of or significant line emission, and the star-forming ones, which do have significant line emission. And remember, again, we are looking for lines, so we just want to exclude all this part and keep the ones that have significant lines, and which is why we choose this cut here. And the second thing is we also use the compactness. So we know that higher redshift galaxies are more compact, and so we remove those which, by this definition, are more extended. And this then takes care of most of the other samples, and we are left with around 2,000 objects, which is only 0.4% of the initial sample size that I started with. Okay, so after we remove a bunch of sources and actually detect or find the objects which have emission lines, then we can go and compare or just determine whether we have an EGN. And this is determined by the broad component of the model, so of a two-component model, and only if the full width of maximum is larger than 1,000 kilometers per second can we say that this is an AGN. And yeah, so we compare two models, one with just one Gaussian and a narrower full width of maximum with a two-component one where we have a combination of the narrow one and the broad one. And only if this one is the best fit, which we determine with the Bayesian information criterion. I will not go into detail. If you want to know what this is, you can ask me. And yeah, if this is the best fit and the full width half maximum is larger than 1,000 kilometers per second, we put it in our broadline AGN H-alpha candidates. The stress is on candidates. Yeah, and currently I have 36 of these. So I want to point out a subset of this sample that I found, and we have heard about this already yesterday and today. So there is a significant fraction that shows weird profiles which are very isometric. And so if you just look at this fit with two components, you can clearly say that this is not a representative. So, but with the current spectroscopy and the data that we have, we cannot say what is the physical nature of these objects. So I cannot tell you if this is interacting galaxies or this is dual AGN or if this is absorption or whatever else you can think of, but I need spatially resolved spectroscopy to disentangle these effects. Okay, and the last thing I want to say is what comes next, because as I said, we have this confusion between high redshift H-alpha and low redshift contaminants. So the question is, how can we distinguish these two? So there are a couple of ideas that we are thinking about. So we could use other colors, for example, the UV, the rest frame UV, and do a bit more color selection, or we can fit the SCD with and determine from the photometric data, determine the redshift and compare it with the spectroscopic one. However, this is not so. This photometry stuff. Maybe you notice I don't really trust, and the last thing we are thinking about is comparing the properties of lines of already known H-alpha and partial alpha emitters and see if we can see systematic differences. And the last thing, and maybe this is the most important of my talk today, is that we have, that has not really been said, is that it's not enough to just find the objects and identify them as high redshift, but I also need to know how many I did not find. Especially because I used all these photometric cuts, right? Because I'm talking about number densities. I cannot interpret number densities if I don't know how many sources I'm not accounting for. That's.
So for the overlapping spectra problem, why don't you just make a perpendicular measurement also?
Yeah, this is a thing that is done in wide field slitless spectroscopy. I don't know why this was not done for Cosmos 3D, but there is kind of something that helps you because this data is taken very weirdly. So in NearCam you have two detectors, and so you take data at the same time in these two detectors, and so the dispersion direction is actually opposite. So this can, I don't know, kind of help you, but I don't know, it's a bit weird.
Additional question? Yeah.
This is really very
Yeah.
You make a selection of compactness. Wouldn't this make you more, like, wouldn't this cause you to miss a gem with galaxy-dominated systems? So how crucial is the compactness criterion in your selection?
Yeah. So we included the compactness. So one motivation really was to reduce the size. But I also developed this criterion when I just started, so I had really no idea what I was doing. And so after I learned a bit more and know also what LRGs are, so this criterion is really strict on these little red dots. So I'm using this for now while I'm developing the entire thing, but this will definitely have to be relaxed. Yes. Yeah.
You only have one line in the spectrum?
Most of the time, yes.
That's hard. Because even the N2
You can barely see them. In most of them, they are barely there. So I didn't say it, but we have fits also with the two nitrogen lines. But they don't match the separation. So I was thinking whether this stuff is actually the nitrogen line, but it doesn't match with the wavelength difference you expect at this redshift.
So your broad components,
Yeah.
is it really true?
Sorry?
Is it really true, the broad component, because the N2 might...
Yeah, this is... okay, so I don't think that if you would have a nitrogen, so they are forbidden lines, right? So they would come from the galaxy part, and they would not be this broad. They would be similar to the narrow. So even if they are there, I don't think that would that would rule out the broadness of the line.
I have a very quick question. So you said you are currently working on the estimation of what could be produced within your sample. Do you have already a vague idea of the purity of your sample?
The purity.
Yes.
Yeah. So we had a comparison with the other group, as I said, because we're doing basically the same thing, but they have different selection criteria. So the only thing I can say right now is that they have recovered like 28 of the objects that I have. So there are like 10 that don't agree with both pipelines.
Purity is a common qualification.
Sorry?
Purity.
Purity. Maybe this term is not used in this field, but we often use this term in galaxy cluster science. About the purity and compactness of the sample.
The reason why you asked.
Yes, but maybe this term is not used in this.
Statistics.